From the forests of Europe to the treeless wastes of Iceland and Greenland, the Vikings, as master travelers and settlers, have faced some of the most unforgiving environments on Earth. Snow, wind, and endless wilderness. And yet, the Vikings thrived. If the modern world vanished tomorrow, the Vikings would still find a way to live comfortably. Their secret? Shelters so well designed, they've stood the test of 1,000 years. Survival wasn't a choice, it was a craft. Every branch, every stone, every strip of turf could mean the difference between life and death. This video details 6 incredible shelters obtained directly from real Viking architectural principles, from quick 2-hour hideouts built before a storm hits, to sturdy long-term winter shelters that could withstand months of harsh northern cold. Each design tells a story of how the Norse adapted, engineered, and thrived in some of the most unforgiving environments on Earth, using nothing but what nature provided. The Tjeldskjol tent shelter is the rapid response shelter designed for immediate deployments during sudden weather shifts or an unexpected night in the wild. It is inspired by the necessity for quick, transitory camps used by Viking factions during raiding or land-based expeditions. The goal is maximum protection from downpour and wind exposure within a minimal time investment of 1 to 2 hours. The builder must first locate 2 sturdy trees or securely drive 2 heavy poles into the ground to act as upright supports. A strong, horizontal ridge pole, or Tjaldas adaptation, is secured between them, ideally at chest height to allow for internal headroom. Rafters, Tjalspera adaptation, are then angled from the ridge pole down to the forest floor. Adapting Norse principles of layered roofing, the critical element is covering the rafters densely to ensure complete water shedding. This involves laying thick layers of evergreen boughs, large sheets of bark, or broad leaves. The layering must start from the bottom and overlap upwards, much like the structural preparation for a sod roof, to ensure water runs down and off the structure without seeping inward. A final strategic step is building a simple windbreak wall opposite the lean-tos opening to deflect prevailing winds. This shelter's primary strategic advantage is its speed and singular focus on providing immediate overhead and rear protection. The traditional Tjeld tent frame, structurally robust and adaptable, is known from archaeological finds such as the Oseberg and Gokstad ship burials. This shelter is designed for portability and maximum structural integrity. The Tjeldverde A-frame, appropriately built, offers the highest structural strength for its weight, enabling it to withstand high winds and hold significant loads of heavy insulating material, unlike simpler shelters. Construction begins by cutting 3 main crossbeams to form the primary A-frames. Careful attention must be paid to the structural geometry, often requiring the use of the Pythagorean theorem to calculate the correct angles and ensure maximum usable interior volume without sacrificing stability. Simple fork joints or saddle notches are employed where the uprights meet at the apex. A sturdy ridgepole, Tjaldas, connects these peaks, running the length of the structure. While historical tents used heavy linen fabric, the modern bushcraft adaptation utilizes natural sheeting. The key is to employ thick layers of bark, cedar or pine, or split logs, overlapping them entirely to create a waterproof shell. This natural layering mimics the function of the birch bark layers that historically provided the essential moisture barrier beneath heavy sod roofs. This robust structure's main advantage is its defined shape, which actively resists strong winds and can support the weight of heavy insulating snow or thick boughs far better than less structured designs. This shelter represents the transition from a temporary camp to a medium tent outpost suitable for several days to 2 weeks, where thermal stability becomes essential. It draws inspiration from the construction of Viking longhouses, which often utilize timber framing with infill walls. The goal is superior insulation and robust wind sealing through the strategic use of composite materials found in the environment. A robust A-frame timber structure is erected, similar to the Tjeld, but with a crucial geometrical refinement observed in Scandinavian bushcraft. The rafters on one side must extend fully to the forest floor to maximize interior volume and create a more expansive, more usable space. The walls are constructed using the wattle technique. Flexible, green saplings like hazel sticks are used as upright stakes, and horizontal sticks are woven tightly between them. These woven hurdles create a rigid base that is then insulated. This base is packed with a mixture of clay, mud, and grass or straw, known as daub. This packing drastically reduces air permeability and adds significant thermal mass. To ensure the long-term integrity of the clay-packed walls, a significant roof overhang must be built to keep the walls dry and prevent the daub from washing out during heavy rains. This design's technical strength lies in creating uniform, tightly woven walls capable of handling the substantial weight and rigidity of the daub mixture. In regions with extreme cold and scarce or unreliable wood resources, Viking builders often turn to the earth itself. Bermed housing and semi-subterranean pit houses, such as the Gruben house found in medieval archaeology, exploited the planet's thermal stability. This approach leverages the ground's stable temperature below the frost line, minimizing exposure to external temperature swings and maximizing wind resistance. A site that is well drained and safe from flooding must be chosen. The builder digs a shallow, sub-rectangular pit, typically around 70 centimeters deep, slightly larger than a prone individual. The excavated dirt is then strategically used to bank or berm the edges around the hole, raising the effective height of the walls and increasing insulation. A low, simple roof frame, often a low A-frame, is constructed immediately over the pit. This frame is then covered heavily with the excavated soil, thick layers of leaves, and moss. This layered earth acts as thermal mass, keeping the interior warmer during winter and cooler during summer. Access is controlled via a small, low-profile entrance ramp or tunnel, which minimizes heat loss every time the occupant enters or exits the shelter. The primary advantage of this design is its exceptional temperature regulation and natural integration into the terrain, offering unparalleled protection from high winds. The Torfbeskau, or Icelandic turf house, is the ultimate expression of material adaptation in the Viking world. It was born from necessity in treeless, volcanic environments. This strategy is designed for long-term habitation in cold, wet environments where superior insulation is the highest priority. It is a structure built for longevity and maximum defense against the Nordic climate, utilizing sod and earth as its primary protective shell. The process begins with laying a sturdy stone foundation. This step is essential as stone prevents ground moisture from penetrating and compromising the wooden framework and the turf structure above. Using minimal timber resources, a low wooden frame is built upon this foundation. The most distinguishing feature is the layering of walls and roof. Blocks of sod or turf are cut and applied in exceptionally thick layers, often up to 2 feet thick on the walls. Historically, the waterproofing secret was birch bark, laid beneath the sod on the roof boards. The sod's weight, up to 500 kilograms per square meter when wet or snow covered, compresses the underlying log walls, making them drought-proof and anchoring the waterproof layer. In a survival setting, if birch bark is unavailable, the builder must substitute thick, overlapping sheets of large bark or tightly packed clay/mud as an internal moisture barrier before stacking the sod. The proper technique requires stacking turf blocks with the grass side down first, then alternating layers to maximize structural strength and thermal defense. Skil. This shelter is an adaptation of the central hearth or long pit, which was the heart of the Viking longhouse, serving as the source of light, warmth, and cooking. This construction focuses entirely on maximizing internal heat efficiency and managing smoke flow. The strategy is fire integration and heat retention. The structure is purposely built low and small to be heated rapidly and maintained efficiently by a robust, stone-lined fire pit. The initial structure is small, log-based frame. It uses log cabin principles for the foundation, but only 2 logs high, allowing the timber frame roof to extend close to the forest floor. This low profile drastically reduces the total internal volume, making heating extremely efficient. A rectangular pit, typically 4 feet long and 2 feet wide, is dug in the center of the structure. This pit is then carefully lined with large stones from the nearby environment. The strategic use of the pit's excavated clay mixed with water is then employed to seal the gaps between the rocks, securing them and creating a homogeneous, robust hearth. Once dry slightly by a small initial fire, the stone-lined pit acts as a crucial thermal mass, holding a radiating heat long after the fire has dimmed. A small, specific smoke hole must be positioned directly above the center of the long pit. Since the fire is low and central, the smoke is drawn upward efficiently, ensuring that breathable air remains available near the sleeping areas. This structure offers superior internal heating capability due to the efficiency of the stone-lined pit and the maximized thermal exchange within the small interior. Before the first log for any shelter is cut, the most important survival decision is the choice of location. The Vikings depended heavily on what can be termed the rule of passive defense, utilizing the natural landscape to perform most of the work required for protection. A hillside could block the wind, a river bend could guard their flank, and dense forest could hide their camp from watchful eyes. The Northmen didn't fight nature, they built with it. A rigorous evaluation of hazards and microclimate optimization is not merely good camping practice, it is a critical, life-saving strategy inherited from the Vikings' expeditionary movements. Historical records suggest Viking factions often established transitory camps for processing goods or temporary occupation. A poorly chosen location, even for a single night, risked serious hazards like exposure, injury from falling debris, or disease spread by insects. The builder must first determine the prevalent winds in the area. Wind flow dictates where the rain will blow and, crucially, where the shelter's warmth will be stolen. By positioning the shelter entrance or sealed sides to block the dominant wind, the builder maximizes heat retention and minimizes the risk of drawing smoke into the living space. Furthermore, the area must be cleared of potential hazards, specifically falling trees and dead branches, known ominously as widowmakers. If these cannot be avoided, they must be proactively cut down using tools like a survival hatchet or saw. Finally, hydrological risks and insect populations must be managed. A breezy location is preferred, as bugs avoid exposed areas. The necessity for precision in choosing these temporary locations demonstrates that the Vikings treated temporary camps with the strategic rigor usually reserved for permanent shelters. Simple but effective hand tools are required to construct shelters with the durability and structural integrity of the Norse tradition. The axe is essential for felling wood and creating structural notches. The saw aids in precision cutting. It is used for advanced joint work, especially for structures meant to last weeks or months. A hand auger drills precise holes for robust wooden pegs, eliminating the need for complex lashing or modern metal hardware. The Vikings' secret to building shelters that lasted centuries was their deep understanding of nature's raw materials. Every timber, every beam, was chosen with purpose. They understood their materials so well that a single season of labor could create shelters that stood strong against countless winters. Build once, maintain little, and let the North remember your craftsmanship. Viking builders used complex, load-bearing joints such as mortise and tenon, even in non-permanent structures, demonstrating a commitment to rigorous engineering. In a survival adaptation, this translates to mastering simple but effective joints. Techniques like saddle notches, commonly used in log cabin foundations, provide mechanical strength that locks the structure together. For structures requiring immense load-bearing capacity, such as those supporting heavy turf roofs, a hand auger used to drill holes for simple wooden pegs creates hardware-free joints. These joints maintain structural integrity under intense pressure, a vital factor when materials are scarce and failure is not an option. Long before modern bushcrafters ever touched an axe, the Vikings had already mastered one of the smartest survival secrets: preserving wood with fire. By lightly charring the ends of logs before driving them into the ground, they turned simple timber into waterproof anchors that could withstand decades of rot and frost. It's a method so effective it still inspires techniques today, from the Japanese shell-sugi band to the fire-hardening tricks of wilderness survivalists. The physical result of charring the wood is twofold. The intense heat drives out internal moisture and creates a sealed, protective layer of carbon. This dramatically increases the wood's resistance to rot, decay, and insect infestation, extending the foundation's lifespan when set in damp earth. This strategic investment of time in the upfront building phase eliminates the need to expend critical energy rebuilding a foundation that has rotted prematurely. The Viking style builder views materials not as temporary fixtures, but as engineered components designed to fail slowly. Insulation is the final line of defense against the climate. The Norse tradition provides methods for superior sealing: wattle and daub. The combination of woven sticks, wattle, packed with insulating materials like clay, mud, and grass, daub, creates a composite layer that offers thermal protection superior to bare log walls, effectively sealing drafts and creating thermal mass. Layering and banking. In rapid survival scenarios, dense layers of dead, decaying leaves, pine needles, or moss can be banked against the external walls and roof rafters. This practice provides rapid insulation, effectively fills gaps, and prevents drafts, turning a porous structure into a functional safe haven. The fundamental principle derived from Norse material science proves that a shelter is only as good as its weakest seal. Proactive engineering and meticulous sealing are essential for maximizing survivability. The 6 shelters outlined, from the quick chilled skeel to the highly insulated long-term torfbear, demonstrate the strategic depth of Viking architecture. Survival in the wilderness, mirroring the challenges faced by the Northmen, is not a matter of instinct but results from rigorous strategic planning, resourceful execution, and the ability to adapt historical wisdom to contemporary environmental constraints. To begin mastering actual Nordic survival, the strategic decision is critical. Evaluate your environment, assess your time frame, and select the shelter that best adheres to the resourceful, durable mindset of the Northmen. Gear up, plan your site, and build your fortress.